today about energy and the environment, also about medicine, and a bit about cultural heritage preservation. So what you see at the bottom right here is a needle that's being inserted in a brain by a neurosurgeon. And the goal is to go and treat Parkinson's disease, or rather, we cannot treat Parkinson's disease, but we can alleviate the effects by inserting an electrode that goes and stimulates a certain area of the brain. And that stimulation is going to alleviate the shaking that is traditionally observed and usually observed in Parkinson. So the idea, of course, is that when you insert the needle as a surgeon, you would like to make sure that you insert it as close as possible to the optimal position so that you excite the right area of the brain and not any other area that you do not want to excite. So this is the basic idea about the simulations that can be done in medicine. So what you see here is a real-time simulation of the insertion of the needle and the retraction of the cannula, which is used in order to make sure that the needle and the electrode remains in place. There are many complexities. I'm not going to talk about this today, but that gives you an idea of why it would be a disaster from a certain perspective if the needle were to be inserted in the wrong place. So those are the partners that we work with. So as you can see, we work with about 15 to 20 different engineering companies in the world. And we were funded by most of the research councils in Europe, as well as international research councils. So this is also interesting for you, I guess, because from Korea, Luxembourg is very small. Also from Europe, Luxembourg is very small. It's an extremely small country, 700,000, maybe even less inhabitants, 500 to 700, depending if you count people coming in and out from the neighborhood. So you can see Luxembourg here in the very center of Europe. This is the center of Luxembourg. This is the industrial and third sector district. Wine is being grown here. This is a parliamentary democracy with a Grand Duchy. This is the only Grand Duchy in the world, actually. And it has a very high GDP per capita. It's number 2 after Qatar, if the numbers have not changed. And it's a super international place with people coming from everywhere in the world. As you can see, there are a huge number of researchers that are not Luxembourgish, 80%. In fact, there would be ways to increase that number. And there are here many in European institutions. As you can see, very stable government, and it is a super welcoming place, which I encourage you to visit, and I hope that we can make that happen after my visit to Korea, which unfortunately could not happen this time. And thank you so much for inviting me to do this. So I will skip the end of this presentation, this movie, in order to go into the most interesting part. I just wanted to tell you also that we have one of the biggest HPC in Europe, in Luxembourg, which is led by Pascal Bouvry here in the university, and is extremely helpful for the simulations that I will show. And I would like to thank that support, and also to look at this building, because this is a building you will see again in the rest of the presentation. So let me start now by the data-driven patient-specific breast modeling. So this is a problem related to breast cancer. So first of all, we should acknowledge that breast cancer is the most common cancer in women. It kills a very large number of people worldwide, of women worldwide. And it's extremely important to be able to either cure this cancer or find ways to avoid it. So what you see here is one of the Luxembourgish European institutions, which is called the European Investment Bank. And we were at the conference in 2019 with my PhD students, Arnaud Mazier in the white chart here, who is walking around a guy in a suit. This guy in a suit is one of the economists of the European Investment Bank. And what we are showing him is the ability that we have to gather immediately using only a 3D point cloud acquisition using LiDAR on a very simple and low cost device to be able to show what he looks like from outside in a few seconds. And this is basically what we are going to use. So we are going to use point clouds for real-time geometry acquisition. And from there, we're going to then start simulating what happens in the body of the patient. So let's assume now that a surgeon needs to remove part of the breast in order to get rid of the tumor. So this is an operation which is quite standard. However, it is quite difficult to do. So I'm going to try to be as clear as possible, as I looked at the title of the talks in the conference, and there were not many talks about medicine. So I'm going to explain as much as I can without jargon so that you can follow what I'm talking about. So here is a pre-operative image. That means that before the operation, the lady is lying down in an MRI, and an MRI, so which is a particular type of image, is taken in order to see where the tumor is located. And during the surgery, as you can see, the lady now is on her back, and the surgery can take place. Which means that if the tumor was at a certain place, a certain location here in the breast, in the left-hand side of the slide, on the right-hand side, because of the change of gravity, gravity is now applied from top to bottom, and in the other case, the breasts were in the downward direction. So of course, there is a change in the position of the tumor due to the change in position of the patient. So the basic idea is, how can we try to figure out before the operation where the tumor is? This is where you see the arrow in the black picture in the middle. And how can we predict where the tumor is going to be after or during the surgical operation? So this is the basic question that we're trying to answer, so that then we can put some sort of virtual reality glasses on the surgeon, so that the surgeon can actually see through the patient and see where the tumor is and can go and remove it safely without removing too much of the breast. So this is the basic requirements for the simulations we want to make. This is a multidisciplinary simulation because we work with biologists, with modelers in mathematics, computational mechanics people like Chang'e Li, who was my PhD student in Cardiff and worked in that field with me, and also computer science, obviously, because we want to have a fast method, which is easy to use. We need a very nice interface, and we need to solve on computers that are sufficiently optimized for the work to be done properly. So how we're going to do this? So we have the lady the patient laying face down, and the idea is to transform this position into the face up position. And in order to do that, what we have to do is remove the gravity. So this is the first thing we do. So we just assume that the patient is in the space station, which means that we do an inverse hyperelastic simulation. We try to find the reference configuration, which is unloaded without any gravity. And then we will apply the gravity again, but now in the other direction, in order to compensate for the change in position of the patient. So that requires a certain number of assumptions. First of all, that we have some sort of model of the breast. In that case, we use a hyperelastic model. That we have the geometry of the breast, which is given in the MRI picture, which we use as a base. And that we know material parameters, which is also very difficult because these material parameters vary from one woman to the other woman, and also vary during even 1 month for each and every woman due to the menstrual cycle. So essentially, everything is unknown. The boundary conditions are also unknown. And the question is, how can we make simulations when we have so many unknowns? And this is essentially a question which I think goes beyond medicine, and that is why I give you 3 examples today. And that probably is quite useful in other applications of disaster prevention, because most of the time we won't be able to measure everything, and there will be always some sort of unknown model, geometry, parameters, boundary conditions, or everything together. So let's see how we do that. So first of all, we start from a medical image, and then we end up with something that we need to be able to use for finite element simulation. So now I will assume that the audience has some idea about finite elements. This is a method where you discretize the system into tetrahedral elements or hexahedral elements. So essentially small and simple shapes that you can then use in order to store the unknown field. For example, here, the displacement field, the strain field, the stress field, and the forces. So the way we do things is that first we find the initial configuration, as I said before, without gravity. We then apply gravity in the proper direction. And at the same time, we need to identify the material properties, the boundary conditions to make them more precise, and the material model, because the material model a priori is not known. So we have to make certain assumptions. And then on the fly, we want to be able to identify these parameters and ultimately even the model. So in this particular case, we identify only the material parameters, but our goal in the long term, and this is something that I find personally very interesting, is to identify the material model in the form of model form uncertainty on the fly as we gain more information from the surgical field, for example, using cameras, stereoscopic cameras, or any other device like ultrasound, for example. So this is what we're doing. And so the results today are such that we are able to do these simulations in real time. So it takes a few milliseconds to compute. The procedure is very flexible because we can do that for any patient that comes into the operating theater, and it's very fast. The acquisition of the data takes only 1 minute or 2. And it's already tested within clinical settings because some of the surgeons that we work with have tested this. And it's very accurate in the sense that we can get to sub 3 millimeter accuracy, which is quite good, knowing the fact that we do not have any preconceived idea about the model and parameters that we want to use. So then if you look at the details of the simulation, let's assume that we start at the top left. So we will measure the prone configuration, which means face down. Then we will compute the undeformed configuration in the middle at the top. We will then apply gravity towards the interior in order to now compress the breasts due to the fact that the gravity is now acting, let us say, on the breasts directly that are not resting on the MRI table. And then what we do is we compute this deformation, and we compute that and measure the mean absolute error, because we have measured supine configuration, which is given by an image that we can measure using point clouds, for example. And we compute the difference between what we estimate at the top right and what we measure at the bottom right. And now if we have a maximum absolute error, mean absolute error that is less than some number, we stop and we say that we have found the optimal prone configuration. And if not, then we go back to the original and we keep applying gravity until we find the proper shape. And that goes surprisingly fast. This is actually the example, so I don't show you the whole simulation because it's a bit long. So I selected, if it decides to start, yes, the end. So what you see is the deformation of the breast under gravity, and you see that there is some adjustment. The nipple is used as a tracking device in a certain way to make sure that there is some consistency in the deformation. And you see that there is some oscillation until you converge to the proper solution. And after a few iterations, the convergence is ensured, and you see now that you have the deformed shape of the breast in the lying on the back position, and that can be used for the surgeon to compute the location of the tumor inside using, for example, virtual reality, which we haven't done yet, but this is the next step. Okay, so what's the conclusion of that part of the presentation? Well, it's that we have partial model information and system-specific identification, real-time fit of the error, and that we are able to do that really fast. So now I'm going to show you a completely different application, which has in common the fact that we are using data in order to update the model that we are starting from. And this application is a data-driven approach for urban wind harvesting, which is led by Marie Curie fellow Anina Sarkic-Glumak, who is in my team now for a few years. And I will now tell you a bit about the idea. So the idea is that we would like to generate energy using buildings. So you can see here the Bahrain World Trade Center, where you have some wind turbines that are located in the center here. And in fact, there was some problem because of the ill configuration of those wind turbines. The optimality of the wind energy harvesting was quite low, in the sense that they could have been placed in a much better way in order to optimize the energy harvesting in that particular place. So the idea is to ask ourselves questions such as, what if we put wind turbines in urban environment? How would that affect the urban comfort, for example? And how can we optimize both the urban comfort, the noise, the amount of wind that is being felt between buildings, and how can we generate the optimal amount of energy by putting the turbines at the optimal place? As you can imagine, if you take the bottom right figure, if you put a wind turbine on the left building, it will have an effect on the middle building and on the right building, because there will be a wake at the downstream of the turbine, and that will affect the efficiency of the turbines that are downstream. So we would like to be able to calculate this as fast as possible and to use data that is being acquired in real time in the city, for example, using sensors, in order to optimize the position and the orientation of the turbines, for example. So this is the idea. We would like to have locally generated renewable energy, because we don't want to transfer and transform the energy. We would like to have a technological solution such as wind turbines in a built environment. And we, of course, now need to be able to perform wind flows simulation, because if we want to optimize the position of the turbine, we need to know what are the boundary conditions. And again, here, as in the previous case of the breast, the boundary conditions are not very well known. And we need to focus on certain quantities of interest, which are in that case wind speeds and wind direction characteristics, as well as turbulence. So that project, Data for Wind, is trying to combine computational and experimental wind engineering data. We are working with some of the best people in wind engineering from the experimental angle in various places in Bochum and in the Netherlands. And we would like to be able to predict the flow patterns within complex urban wind canopies. As you know, probably, there are therefore two approaches that will be used here: experimental and computational wind engineering. So from the experimental side, we can look at actual flows, but from the computational side, the issue is that we can only look at simulated flows around simplified really models of buildings. Experimental wind engineering is very costly, and we need to do it specifically for each scenario. There is a lot of expertise that's required in order to know what is the incoming wind profile. So again, the boundary conditions, what wind is going to come in the city. And also, it's very difficult to monitor quantities of interest in the wind tunnel, because we need large control volumes, and this is difficult to do in practice. So in computational field, we have completely different settings where it's much easier to include different geometrical and boundary conditions. We can look at different scenarios easily. We have reliable solutions. However, they probably will require very high computational costs, for example, LES. And that's going to be either very efficient or very accurate. But usually we don't have efficiency and accuracy at the same time. And this is what I'm going to talk about next. So this is the basic idea. We have CFD, computational fluid dynamics, wind tunnels, and the idea is to use the wind tunnel models to assimilate this into the CFD simulation. And the idea is then to have reliable predictions of quantities of interest, such that you can deploy the wind turbines. So first of all, we will do data assimilation, as I said, and we will therefore include experimental knowledge, which is observation, into the computational model, so that the models can adapt to the actual situation in the field. That will improve the predictive power of the models. And that data-driven approach that we have here will build on the strength of both wind tunnels and numerical simulation. So how are we going to do it? So what we do is very simple. We use large eddy simulation. So this is a quite expensive simulation technique for turbulence. I don't have time to go into details at all. And we would like to validate LES, so essentially assimilate as much data as we can from the wind tunnel. This is what you see on the left-hand side. And then fit, using machine learning, the runs or the KW or K omega or whatever other model that we could have, which is low cost, fit this on the validated LES such that we can essentially have a cheap, meaning runs, simulation with the accuracy of the LES by using machine learning approaches. So essentially what's done is that we learn the run solution from the LES solution. Again, this is a very schematic presentation that I give you today, because the idea is to stimulate discussions with you. And in order to get more details, it would be necessary to look at the papers, which I can provide very easily, and in fact that you can find on the web page below, which is identified at the bottom of all the slides. And don't hesitate to contact me as well. So this is basically the end of the second part, and I would like to finish by a really exciting project that is led in collaboration with an archaeologist and a historian, Professor Andrea Binsfeld, with Dr. Pratik Suchte, who is working on meshless methods, and our PhD student, Juan Aguilar. And this is about archaeological digital forensics. So this is about forensics. What happens when we go on we could call it a disaster site. In that case, this is not exactly a disaster site because the disaster did not take place last week or last month. It took place over hundreds of years. I'm going to try to explain this to you. This is the Tel Nebi Yunus in Mosul, in Iraq. And the idea there is that there was a mosque, which is centuries-old cultural heritage place, and it's a place of worship. It was severely destroyed by what is called the Islamic State from 2014 till 2016. So you can see here the remnants of this place with a few pillars that are conserved outside, but most of it completely destroyed. So what Juan did is that he went there and he saw that there is an ancient palace which is not excavated and still underground. It is very severely deformed. So you see here a tunnel. There are some tilted walls, slanted floors, and cracks, a bit like after an earthquake. And this is how things worked out. And the question is, if you go back in time, you see on the right-hand side, you see today. And in the back, on the left-hand side, you see what we think happened in the past. And the question is, can we go from what we see today back in time? So can we basically build some sort of reverse time machine that will bring us back to the past, not bring us back to the future in that case? And so, of course, there are many solutions to this. And because there is not only one set of parameters and models that are going to bring us back to the past, there are many solutions. And this is therefore an inverse problem, which is ill-posed. And our question is, can we look at what we see on the right-hand side and guess what happened in the past? What were the sequence of events that led to this? In which order did things happen? So those are the basic research questions. The computational research questions are that when you do a 3D scan of this using LiDAR, you know very well that you end up with billions of points. And these billions of points you cannot use directly because it would be far too computationally expensive, especially if you want to do environmental simulations using acoustics, which we are doing with other colleagues, or thermal simulations for buildings, for example, for smart buildings or building infrastructural models or smart cities and so on. You cannot use all the points. So the idea is, how can you simplify this? This is also very useful when you do asset management for oil industry, for example, because you could have, or any industries, if you have some sort of industrial plant and you would like to assess it using drones that will take some sort of 3D point cloud model, you would not like to have a full 3D model with billions of points. You would like to reduce the size of this. And the question is, what is small enough and what is too small? How can you select the number of points that you want to use? And how can you do that in a systematic way and an effective way? And there are many open questions in that direction, including machine learning recognition of certain shapes to simplify the structural model. I'm not going to go into this. I'm simply going to tell you a bit how this research was done. So first of all, it's very difficult to acquire data. It's a bit like when you go to an earthquake site. You go there and you try to acquire data. You have to walk in quite difficult places. On top of that, this is, in that case, a military zone, which means that you cannot enter easily. So all that was extremely difficult. Also, you cannot get material data very easily because there are very limited ways to do site inspections using geotechnical tools, for example. However, this is a very historically important site because it has a huge cultural continuity. So I'm going to tell you very briefly what we think happened. So this is an Assyrian palace, which you see at the top here, with very beautiful winged bulls that you see here on the top of the bricks. And what happened is that it was destroyed. Then, as you can see here, the ground ended up at that height, we think. And then there is a church that was built on top of that. And then from the church was built an Ottoman mausoleum. And then there was some remodeling from Saddam Hussein. And then after that, that was again destroyed by the Islamic State. And now we end up with that, including looters' tunnels, which are these little tongues here going inside the structure in order for the Islamic State looters who are trying to sell things on the black market to go and find some artifacts that were there in the Assyrian palace and sell them on the black market. So essentially, there is lots of changes that have taken place over the centuries. And the idea is to go on site and do digital photogrammetry and point cloud acquisition to try to reconstruct this site and build a virtual reality and virtual version of the site and be able to perform geomechanical simulations. If you go on site, you can see such cracks and slanted floors and broken stone panels, very large cracks, tilted walls. So it's extremely difficult to acquire information. And Juan did that meticulously along all the tunnels with cameras and 3D point cloud acquisition devices based on LiDAR. And he took photographs of most things in order to bring back as much information as possible to build this again. And the question is very simple. How long was, for example, any of the monasteries, for example, how long was that monastery, in fact, standing? When was it exactly destroyed? And how can we find that out based on the deformation that we see today? So can we use the deformation we see today to back calculate the sequence of loading that led to the deformations that are observed in the tunnels when we visit them at the present day? So I'm going to show you now, if you remember the first building, I told you to take a look at the building in the video at the beginning, because this building that I was showing on the video of Research Luxembourg, you can see here on the up right-hand side, this is the University of Luxembourg, one of the buildings. And there is a tower in this building, and we wanted to see whether we could use our scan to simulation technique in order to make a fire simulation for that building. So we assumed two things. We assumed that we could, first of all, get into the building and get the actual 3D point cloud. This is what we did. And then we went into the staircase shaft because there is a ventilation shaft inside the staircase. And when you open the ventilations, you ask yourself what is going to happen to the fire and the smoke, because that staircase is used in order to evacuate people. So you would like to avoid that people would be smoked into the staircase. So you would like to contain the smoke at the bottom as much as possible. So what we did with Pratik Suchte is, so Pratik and Juan went there to acquire the 3D point cloud. And then we performed some simulations. So we see the fire on the left, the smoke in the middle, and in the case of the vents being open or vents closed. So you see the fire is starting and is relatively contained to the first floors. However, when the vents are open, the smoke is sucked into the staircase and invades the whole volume, which is exactly what we would like to avoid. However, if we close the vents, and this was just a proof of concept, you can see that the smoke is being contained at the bottom of the staircase, which is exactly what you would like. So as a conclusion, we were able to really solve that issue, and this is only a proof of concept with low resolution scans, but I think that shows that we can do fire simulations as well with the techniques that we developed. So in conclusion, this was a talk about 3 multidisciplinary case studies of data-driven modeling that we do in Luxembourg. In all cases, we have only partial information and data on the system. We would like to do real-time, if possible, data assimilation and identification. We would like to control the error. I did not talk about this, but this is a very specific thing we do in my team, which I believe very few teams do worldwide, where we can provide an estimate of the discretization error, which means the error performed, done, committed by the numerical simulation, and it therefore give the user an assurance about how the accuracy is in terms of percentage, for example. And finally, we provide open source codes. You can get in touch with me if you are interested in this. It's all on the online. You can also visit our website and follow us on Twitter and Instagram and everywhere else. And you can also be sure that we will soon be releasing new results on scan to simulations, from smart cloud simulations to actual computations. So with that, I would like to thank the organizers again for inviting me today. And I am sorry I was probably a bit long, especially with the hiccups at the beginning. Thank you very much for your attention. I look forward to your questions. Oh yes, now it's working. Yeah.
So when I was in the UK, we also talked about the first thing. So at the time, I just how we see the advance. So is it the real time or we did time to simulate?
So sorry, I cannot hear very well. There is a huge amount of echo and the voice is extremely unclear. So okay, so the question is if the breast simulations are real time now, is that right? Yes, I think that's the question. Yes, I mean, maybe I can use this opportunity to explain what is meant by real time, because this will depend on each application. So for example, if you are thinking of doing surgical training, meaning that the surgeon is using virtual tools to train to do a certain operation, but to do it in a virtual sense, then in that case, you need to be really real time, meaning that you need to have approximately 500 simulations per second. That would be haptic rate, right? So that would be between 500 and 1,000 simulations per second. So 1 millisecond to 2 milliseconds per simulation. So that's for surgical training. If you do surgical guidance, now the operation has started, and you need to give feedback to the surgeon as fast as possible. So in that case, you can be a bit slower than real time, meaning a bit slower than 500 hertz. You could probably be a few minutes You know, if your simulation lasts a few minutes, that will still be okay, because the operation lasts from time to time hours, at least dozens of minutes. So a few minutes to simulate is not going to be so important, so problematic. And then you have the intermediate case, where you are not doing surgical guidance, meaning you are not guiding the operation as it happens, or you are not doing training on virtual patients, but you are doing planning. So you are trying to plan the operation. And in that case, you can simulate for hours and hours, because the problem is to get as accurate as you can with the simulation tools that you have. So you see, you have three different cases. You have training, where the accuracy is not important, but the speed is important. You have guidance, where the accuracy is important, but let's say can be, you can do with millimeter accuracy, let's say. So you can go up to minutes to simulate, and that will be fine. And you can do also surgical planning. And in the case of surgical planning, you have maybe hours to simulate, maybe even days. So this is, you know, this is why real time is in fact quite ill-defined. And when I use the word, I always have to be careful to be precise and define it. And I did not define it this time, because there are many different cases. So in the particular case of the breast that I talked about, we could solve the problem in a few milliseconds. So that was extremely fast. And yes, I hope that answers the question. Great. Oh, thank you so much for this question. It's very interesting. So the question is, are there any advances in automated segmentation in 3D modeling of large structures? So yes, and this is not my specialty. So I can only tell you that the state of the art today, as far as I can see, if you have, so I'm going to talk, I imagine you talk about building infrastructure models, or maybe about, let's say, image acquisition for large buildings and so on, that you would like to monitor over their own lifetime. I will assume this is the framework of the question. So if that is the case, then what I know, thank you, is that at the moment, if we acquire a huge point cloud, we have billions of points, literally. And with the newest scanners, you have even more points. For example, Artec 3D is a company in Luxembourg working on these high-resolution sensing, and you already get huge numbers of points. And the idea would be, how can you decrease that number of points? And then how can you recognize the part of the structure? For example, if you have a beam, can you see it's a beam? Instead of having 1 million points, you see it's a very simple beam. So you can make a very simple structural model using beams instead of having millions of continuum elements. And I know that there is a lot of work done in the artificial intelligence area, especially in image recognition, where researchers are identifying how, based on a point cloud, what is the shape of the structure. So is it a beam? Is it a plate? Is it a cylinder? And how can I simplify that? And how can I essentially create categories in which part of the structures belong? And then how can I assemble these categories like Lego blocks together in order to have a very simplified model as opposed to a very detailed model? So I hope this was the question you were asking. We are working with people in Iran, for example, that are working on this. However, it is still, as far as I know, an open research topic, and I do not know of any particular case where that has been done, let's say, practically speaking, yet. But it's a very interesting topic, and I'm extremely interested in it, in fact. Thank you very much.
Thank you for the presentation, Professor Bordas. Again, give him a big applause.
Thank you. Thank you very much. Should I? Okay, thank you very much. I will stop the video and the screen sharing. Thank you very much again for the invitation. I really appreciated the time that you gave me. Thank you. Yeah.
Okay, we have a happening play, and then we continue to last session. So we'll start unfortunately.